chapter 7. So, ooh, nice job. Okay, chapter 7. So this is on work, kinetic energy. So what is energy? Yeah. Okay, the ability to do work. That's one very important thing. In what ways do you see energy in your life? Right now, I'm exerting a lot of energy right now. Am I doing work? Why? Nothing's happening, right? Nothing's changing. Okay. Now, if I were to do that for a long time, it would eat up and have a calorie consumption, and I would eventually need to eat more frequently, and I would get worn out after a while, right? That's energy consumption. Okay, but it's not necessarily the way we're going to talk about energy today. Okay, so what else? I mean, what ways do you see energy? Yeah. Power bills. What are power bills? What's a power bill? Well, you or your parents have received them. Okay, so you use energy, right? We get a power bill, but it doesn't say energy bill, it says power bill. And we talk about clean energy all the time. Power is essentially you can think of as the consumption in a function of time of energy, right? We talk about green energy. What are we saying when we say green energy? Yes. Okay, renewable energy. Okay, good. Anything else associated with that?
Solar power.
Sorry?
Solar power.
Okay, solar power, so the specific types of renewable energy. We also talk about reducing the rate at which we consume energy, right? And we talk about energy that will be useful for not killing trees and stuff like that. Well, actually, put more carbon dioxide in the atmosphere. Okay, so I want to point out one very important thing. Carbon dioxide makes the atmosphere warmer. If you go to Venus, it is 860 something degrees, night and day. It's hotter than Mercury during the day because it's 96% carbon dioxide. It's the same temperature night and day. Carbon dioxide makes the atmosphere warmer. I hope you'll come away. If you remember nothing about this course, carbon dioxide makes the atmosphere warmer. Okay? So, there are very few scientists that dispute that. So, now, so kinetic energy. So let's talk a little bit about kinetic energy. Okay. What is kinetic energy? Yeah. Okay, it's the energy associated with being in motion. That's right. So if I am moving at a particular velocity and I collide into something, right? And if I tackle someone in a contact sport or whatever, I have my energy is being used to do something. So there was a very interesting, so if I just said k is equal to 1/2 mv squared. They give an interesting example in Waco, Texas. Waco, Texas has had a lot of interesting stuff. I can see why they call it Waco, Texas. But what they did is they took trains. I'm going to do my best here to make a real train here. They took trains 6 kilometers apart. I can only imagine what this must have been like. The guy who was doing this, then he had a crowd of 30,000 people in the middle. They were 6 kilometers apart. He put the throttle full open on both sides of this, 6 kilometers apart. They accelerated at 0.26 meters per second squared, and then collided in the middle. So they do a little bit of a calculation here. So tackle football is one thing, but 100,000 kilogram trains colliding is another thing at high speeds. So let's do this calculation. So let's see how much energy. So initially, what these are going to do is these are going to be these are starting from 0, which we would associate with the kinetic energy of 0. But they're accelerating because there's a force being exerted here by the track on the wheel through friction. And then by the time they get to this point, they are going about 40 meters per second, almost 100 miles per hour. Okay? They hit at 100 miles per hour, and their kinetic energy is changed into collisional energy. So let's consider how much that is. Okay, so if the acceleration, and we're just going to use simple things so that we can do it all by hand, is 2.5 meters per second squared. The mass, well, they give the weight, and I'm just going to assume that it's 1 meganewton. So they actually say 1.2 meganewtons, but we'll just keep it as it is. And the distance is, the distance to the collision is 3 kilometers. So how will we find the final velocity by the time they collide? Sorry? Okay, so we can use v squared is equal to v initial squared plus 2a d. Right? Now, v0 squared is 0, right? So we see that v squared is equal to 2 times 0.25 meters per second squared times the distance of 3,000 meters. Okay? So this means that v is equal to the square root of 1,500 meters squared per second squared. So we see that this is, and I'm just going to approximate that as 40 meters per second. Okay? So, because I've basically only given you one significant figure. Okay, so these things are moving about 40 meters per second by the time they collide. So, now how are we going to find the energy of space? So what we're going to assume is that this kinetic energy then all becomes, just has what we call an inelastic collision, and we're going to assume that all of the energy is then changed from kinetic energy to this whatever other forms of energy. So how do we do that then? So what would be the total energy that we would have by the time these, right before they collide, what would be the kinetic energy of these two things? Yes? Okay, 1/2 the mass times the final velocity squared. So what would the mass be? Okay, so this is the weight. Okay, good. So we'll just use the approximately 10. And so we'll say that this is, but there are 2 trains, right? So we have to take 2 times 1/2 times the mass of the train, which is just going to be 1 meganewton divided by G, which we're going to assume is 10 for the moment. And so we're going to get 10 to the 5th kilograms. Times the velocity squared, which is just 1,500 meters squared per second squared. Right? So what does that give us? That gives us 1.5 times 10 to the 8th kilograms meters squared per second squared. Now this is actually, this right here, this kilograms meters squared per second squared, is what we define as the joule. So we say that this is 1.5 times 10 to the 8th joules. Now in reality, the mass is a little bit heavier. It was 1.2 meganewtons. And so this mass was bigger. The velocity was actually a little higher because the acceleration was slightly larger. And it turns out that, and since we're just doing one, this is essentially 200 megajoules. Okay? Now, 200 megajoules. Does anyone know how much energy is in a stick of TNT? About 1 megajoule. So this is the equivalent of 200 sticks of TNT. Now, a lot of people died. Well, several people died that were spectating at this event, and hundreds were injured from flying debris. But it was a pretty catastrophic. But really, it's only about 50 kilograms of TNT. That's the equivalent. But 50 kilograms of TNT is a lot. For example, the bombs on Hiroshima, they were actually considered to be about 9 kilotons of TNT. So just to get an idea of how explosive, for example, or how powerful nuclear and atomic bombs are. And the biggest bomb ever exploded was about 100 megatons of TNT. So anyway, terrible stuff. So anyway, I thought that was an interesting, kind of strange example, but also kind of fun, I guess. Okay, so now let's consider work. Work is defined as so let's consider first work by a constant force. Okay? Now if I look at the definition of a joule, which is a kilogram meter squared per second squared, and I look at that, and I just look at the units for a second. Okay, we can see that we have something that looks like mass times velocity squared, but if I look at that, I have kilograms meters per second squared times a meter. That's an interesting result, right? Because now you have a kilogram times an acceleration times a distance, right? And actually, if you look at the definition of work by a constant force, that's what it ends up giving to you. Okay, so work done by a constant force is defined as F dotted with D, where D is the displacement, vector, and F is the constant force vector. So when I say constant force, it's neither changing direction nor is it changing its magnitude. Okay? You need to keep that in mind. Okay, so displacement, force, the displacement vector. Okay, so what I could have, now let's suppose I start moving this chair across the floor. Okay? Which direction is the force going? Look at my arm. Which direction is the force? It's the direction of my arm, right? My arm's coming up like this. Which direction is the displacement of the chair going? This way, right? Is the force and the direction of the displacement in the same direction? I'm exerting a force on it now. What's happening to the chair? Not moving. Am I doing work on the chair? No. According to this definition, I'm not doing work on the chair because there is no displacement. Okay, so work is the force if we do work, so it's that force in the direction of the displacement. So if I take an object, and here's the displacement. So for example, it moves some distance d, but I apply force up in this direction. I have to take the component of the force that's in the direction of the displacement. And that's how I'll determine the work done on that particular object. Okay? So, if you need to find out, for example, if you need to determine the work done on an object, you simply find all of the forces, then you sum all of the forces that are relevant in the direction along the axis of the displacement. So, for example, let me do another one here. If I have a box on a ramp, and I have, for example, a tension coming up, and I have mg going down, and I have the normal force. What are the forces that are going to be relevant in order to determine the work done on this box? Will the normal force be important for determining the work? No, right? Because it's orthogonal. It's in a direction perpendicular to the direction of motion. Will a component of the weight will be important, right? Because that will be in the direction opposite of the tension. And if it's moving up or down, then we need to consider which direction it's going. So for example, if this box slides down, even though I have a tension going this way, then the force, the component of the gravitational force that's moving that is doing work on that object, and this is doing work against it. And so we just need to find out all those particular terms. Okay. So there's a very interesting relationship that we can see when we look at v squared is equal to v squared plus 2ad. Now, if I look at this for a moment, and I just multiply both sides by 1/2 m. So I just take 1/2 m, I multiply on this side, and I take 1/2 m and multiply on this side. Oops, forgot to put a v squared there. Okay, so now what we're considering is the motion of, for example, this chair moving in one dimension, right? This is an equation of motion in one dimension. What have I written down here? What is this? That's the kinetic energy at time t, right? What is this? That's the initial kinetic energy, right? What is this? Looks like mad, but it means something. Mass times acceleration which is a force in the direction of the displacement, right? So now what we actually have is work. So we can see that 1/2 mv squared minus 1/2 mv0 squared is equal to MAD, or what we would consider the work done on that system, right? So we can see, for example, if the velocity is greater at some later time than the initial time, then that means I had to do work on the system to make its velocity greater, right? If the velocity is less, that means I did work against it and I took energy from that system. Okay, so I did work on the system, or I did work on the system and took it. I can either add energy, kinetic energy, or I can take away kinetic energy. But what this says is that the change in the kinetic energy, remember big delta means change in, the change in the kinetic energy, and let me make this capital down here, is equal to the work done on that system. Yes?
So no work is done if there's no acceleration.
So, I'm going to show that to you in just a minute. And it's a little bit of a tricky thing, but I want to talk about it. Because I can do work on something, but there can be also work being done by something else that cancels it. Not that the work is zero. When I'm pulling this chair, right? I'm pulling this chair, but it may be moving at a constant velocity, right? What is the work? Does that mean I'm not doing work on the system? I'm doing work. What's the problem? There's also work being done by force, by the force of friction in the opposite direction, right? So what I'm putting into it, force of friction is taking out of it. And so I'll talk about that in just a minute. That's a great question. All right. So let's do a simple example. Let's do a little example of our chair here. So if I look at this, I'm going to approximate the chair as a square, right? Kind of a physicist thing to do. And I'm going to say this is 60 degrees here. This is the force that I'm applying on it. And if I cause a displacement d of 1 meter, and let's say the mass of the chair is 5 kilograms. Okay? So this displacement, we have the force here, we have the displacement vector. I'm going to displace it by 1 meter. I'm going to exert a force on it. I'm going to assume that this angle here is 60 degrees. Okay, so what would the work be done? I'm going to assume that this is a constant force that I'm going to be exerting on the chair. What is the work done on this system? Now let's add in all the rest of the stuff. So there's mg, and there's the normal force, right? And force of gravity. Do I need to worry about these? Force due to gravity, force due to the normal force. No, because they're orthogonal to the direction of the displacement. So there's no work that's being done by that. So I do need to worry about this. Okay? So what is the amount of work that I'm doing on this chair if I exert a force on it and move it and displace it by a meter? What do I do? Yes? Okay, so I'm going to take my force. I'm going to take the cosine of 60 degrees times the displacement, right? Okay, so I didn't say what the force was. Let's just say I put in 20 newtons. Okay? So if I do 20 newtons. Cosine of 60 is 1/2 times the displacement of 1 meter. Then I see that I get 10 Newton meters, which is equal to 10 joules. Okay. Now, what would be the final velocity of the chair if we didn't have friction? Let's suppose I'm doing this on a frictionless surface, right? What would be how would I find the final velocity of that chair? Yes? Okay, so I would say the change in the kinetic energy is equal to the work done on the system. And what was the initial kinetic energy? 0. So I started from rest and I started pulling, right? So it's 0. And so that means 1/2 mv squared is therefore going to be equal to 10 joules. So I can solve for V. V is therefore going to be equal to the square root of 2 times 10 divided by the mass, which I said was 5 kilograms. So I just get 20 divided by 5 is 4, square root of that, so that means I'm getting 2 meters per second. All right? Okay. Any questions? You're all happy? Okay, so I just wanted to say, make a couple notes. So the book has a couple cautions, and these are important things. First is to remember that these are for constant force. If the force varies as a function of position or time, you can't use this equation. We're going to derive that in just a minute. And it needs to be a rigid body. And so it's assumed to be a point particle, or that everything moves together. Okay? Second thing, signs are important. If I can have work. For example, if I have something coming and it has some initial kinetic energy and then it slows down. For example, if someone comes and tackles me, right? Then I'm reducing that person's kinetic energy by them hitting me, right? So essentially, I'm doing work on that moving body if I'm stationary. So in that particular case, I'd be removing kinetic energy from that particular system, and so that the work would be negative. So you have to be careful with your signs. Okay? If you're putting energy into the system, you're making its kinetic energy larger, that's positive. If you're reducing its kinetic energy, that's negative. And net work. And this was just something that was discussed earlier. I forgot your name?
Gary.
Gary. So this isn't a network. This is net work. Net work means that after you sum up all of the forces, right, and then you consider what work goes into the system, if you have a force going that's equal and opposite to the force going this direction, the net work is 0. Even if they're both doing work on the system, the net work is 0. Okay? We'll do an example of that in just a moment. Okay, where did I put that? Okay. Any questions? Can't read something I wrote on my piece of paper here, so. Oh, okay. Now, work done by a gravitational force. Work done by gravitational, work done by gravities. Gravitational force. So, we've all done things where we've worked against gravity. When I was younger, I used to like to do Olympic style weightlifting. And what you had to do is, for example, like clean and jerk, you had to bring the weight up and then bring it to your shoulder, then put it over your head. And, I enjoyed that, a little dangerous, a little fun. So, but there's some weird things happening if you think about it, because what you're doing in the end is that your velocity started off as 0, and your velocity ends at 0. Isn't that slightly odd? So what you can think about is that the work is the velocity, the work done by gravity, and essentially the net work done by me against that bar ended up being the same amount because the velocity, the change in velocities are essentially 0. So we have to be a little thoughtful about what we mean here. So now, if I am lifting this chalk up at a constant velocity, right? I'm doing work on this chalk. I have to have a force that's lifting this chalk up. But at the same time that I'm lifting this chalk up, there is a gravitational force going down. And if this chalk is moving at a constant velocity, that means that the work that I'm doing is the same as the work that gravity is doing. Does that make sense? Right? Because the velocity is not changing is not changing over that range system. So let's consider an example here, which I thought was kind of a funny example, or a fun one anyway. So they show Santa in a sleigh on a 30-degree slope being pulled up by a Herculean deer, which I'm going to approximate as a square. A lot of physicist jokes start off by saying we're going to assume something is a sphere. I don't know. The longer you physicists have dry humor, I guess. But anyway, that's funny to physicists, but may not be that funny to you. So here's Santa's sleigh. Here's the deer. This deer is going to take this sleigh, and when this sleigh is going to start at some initial velocity, and by the time it gets to the top, it's going to have the same velocity. Okay, so let's consider what's happening in this particular system. So what are the forces that we have here? Yeah. Okay, so we have gravity. What else do we have? Yeah.
The weight of the box.
The weight of this.
Yeah, goes
This-
that way.
Okay, so I've called that force due to gravity. Is that what you meant?
Sure.
Okay. What else do we have? Yeah. We have the normal force. Anything else? Yeah. Okay, so we have the tension in the rope, right? Anything else? Well, for this one, that's all we have. If we consider the deer, that's all we have. We have a set of forces there as well, but we're not going to worry about that, right? We're just interested in the sleigh. So we know that there's a tension here. We know that there's a normal force. We know there's a tension force. And so what is the axis that we want to do our calculations on? Okay, along the slope, right? One of the things that might have been a little confusing that I realized after last time was that we had a slope, but we were interested, so when we were talking about the car, right? I broke free of thinking about things in this axis, and I said, we're going to worry about that projection. Remember that? Remember how the car was going around a bank? I want to clarify that a little bit. So when the car is on a bank, so for example, a car is coming around like this, and you're seeing that projection, that slice through, and that bank was like that. We were interested in what was the force going along here because it was undergoing circular motion like this. So probably, well, as a kid, I loved to race bikes, and so we had what we call high banks. So basically, you just take the bike around as fast as you could around these corners. A lot of fun. But essentially, what you're trying to do is find a scenario where you don't have to use a lot of frictional force in order to make a sharp turn. And that's all you're doing here. You're coming around the corner like this, and so you're interested in the force that's going towards the center. So that was a different scenario rather than worrying what's happening up and down like this. Okay, so just wanted to make that clarification. But in most of these situations, what we're interested in is the motion along this direction, whereas in this, we're interested in the motion associated with this direction. Okay, so we've chosen our axes, and we can see that we have a tension force, and we have an mg sine theta force that are going to be along the direction where we're going to get displacement. So now what we're going to assume is that this sleigh moves a distance of 20 meters. Okay? So if that sleigh moves a distance of 20 meters, what is the work done by that reindeer on the sleigh? One last thing, the mass of the sleigh is 200 kilograms. Okay? And the angle here is 30 degrees. Okay? So we have an angle of 30 degrees, mass of 200 kilograms. So let's find out the work done by the reindeer in order to get the sleigh, to move the sleigh a distance of 20 meters. So how would we do that? You raise your hand, just a good stretch. Any other? Yes. Okay, good. Now, I want to point out what is F net in this particular situation. Velocity initial and velocity final are the same. Yes. So that means what you can think about is this sleigh started moving, it has some initial velocity, and then it's moving up at a constant speed and gets towards the top. So this is not really what you would think about. It's not like it's starting from zero and getting up to some final velocity. That's a more complex thing because then you need to have forces that vary as a function of time. So this is a little bit of a tricky and very specialized example. But let's think about, so there are actually two forces acting on the sleigh, right? One is the component of gravity down, and one is the tension up. So let's first consider the force due to the tension up, which is as a result from the reindeer pulling up here. Okay? What is that work done? Important part is you can ignore mg sine theta for this moment, right? Because what we're interested in is what is this force doing on the system? Then we can say what is this force doing on the system, and then we can say what is the net work on the system. Okay? So let's first find work done work done by the rate here is what? Yes. T. So that's the force times. Sorry? Okay, good. So, do we know what T is? Yeah. Okay, good. We don't know what T is yet, but we can find it out because it has to be equal and opposite to the force, but we're done by gravity. So let's now find the work done by gravity. Well, that's going to be mg times the sine of the angle, which is 30 degrees, times the distance. Now, is that work going to be positive or negative? Negative. Because this force is in this direction, and the displacement is in this direction. So F dotted with D is the cosine of 180 degrees. Right? So if I take F dot D, right? This is F times D times the cosine of the angle between them. And the cosine of the angle between F and D is 180 degrees. What's the cosine of 180? Minus 1. So we see that this is minus F D. And so what we get that this is a negative times 20. I'm just going to erase that for your calculation. And so we see that this is minus 200 kilograms times 10 meters per second squared times 1/2 times 20, right? So we see that that's just 200, right? 200. No, sorry, 200 times 200, so we get 100 times 200, so we get 20,000. 2 times 10 to the 4 joules. Okay, now what we can say is, well, I don't actually know what the tension force is here, but I can determine that. Well, we do know that there is no net acceleration, so we know that the forces have to be equal and opposite, so we could have used that. But I want to think about it in a little bit different way, which is that the change in the kinetic energy has to be equal to the work done by gravity plus the work done by the tension. Okay? But that change in kinetic energy has to be 0. And so what is the work done by the tension? Oh, sorry, I forgot to put a negative here. That's negative, right? Sorry. That's negative 2 times 10 to the 4th joules, because that's taking away that energy from the system. So that means that the work done by the tension is equal to minus the work done by gravity, which means that that's equal to 200, 2 times 10 to the 4th joules. Okay? So that the work done by each of these forces is the same. Questions? All right. Now, let's do work done by a spring force. This is an incredibly important concept. because it happens in so many things that we do in our life. When we jump, in some respects, it can be considered almost, in some parts of it can be considered harmonic motion. That our legs act a little bit like springs. And everything from shocks to how we interact with things, we often describe that by a spring force. So this turns out to be an incredibly important thing. So we're all familiar with springs. So for example, suppose I have a block that is connected to a wall by a spring. Okay? If I pull this block a distance d, what's going to happen? It's going to pull back. Did you reread me here? Okay, sorry about that. So, the harder I pull, the further distance it gets away, what's going to happen? The stronger the pull of the spring back on the system. Now, if I push on the spring, what's going to happen? It'll push back. So what it means is, if I go one way, if I go this displacement, which is positive, the force is negative, and it's proportional to the distance that I pull it. The further I pull it, the harder it wants to pull back. If I push this way, the force now is this way. So that if the displacement is negative, the force is positive. If the displacement is positive, the force is negative, and it's proportional to how much I displace it. So we can simply write an equation down for that, which is that F, or the force, is equal to minus K times X. Now let me draw, this is a small k. This is the spring constant. This is not the kinetic energy. And this is the displacement in one dimension. So we're really only going to be interested for the most part in terms of springs and what happens in one dimension. If I go this way, it wants to go this way. If I push this way, it wants to go that way. And so that means that's where the negative comes from. The force is in the opposite direction of the displacement. This is the displacement relative to the origin, and this is the strength of the spring, right? A very weak spring would have a very small k. A very strong spring would have a very large k. Now, this is a little bit surprising. This is very different than our constant force things that we have done. In our constant force, we've assumed that the force is the same no matter what position or displacement we are, whereas this says it becomes highly important about where that displacement is. Okay? So this is a very different concept than what we've been dealing with. Now, if I want to take work in this case is not going to be F times the displacement because the force is no longer constant. So we have to do something else. And what we actually use is an integral. Okay? Now, the force, what you can think about is over a very, very, very small interval, we can assume that we have that kx, right? And so we can assume over that very, very, very small interval, we have kx, and then we multiply that by its displacement, right? You can think about F times d, if you want to think about it in that way, that we have that force times that little tiny displacement. But if we want to add up all of those contributions, then we take the integral of minus kx dx. Okay? Where this is now the force, but now instead of doing instead of doing large d's, we have to break it up into infinitesimals that are extremely small. Okay? And then we sum up all of those contributions and then we get the complete work done by the system. So this is how we do it. And now you can see this is easy to do. We've done this a million times. We get minus 1/2 k x k times, let me make sure this is x final squared minus x initial squared. So if we assume that xi is equal to 0, then, in other words, what we're going to assume is that the initial position of the spring is the origin, then the work done by the spring is going to be minus 1/2 k x squared. So all we've done is we've said that the initial position of that spring that we've drawn here, we can say is right here. At that point, there's no force on it, right? So we can displace it by a distance x one way or the other. Okay? Questions? All right. Okay, let's do a quick example. So let's just suppose I take a block here that's mass 1, the mass is 1 kilogram, and it's moving at a constant velocity of, say, 1 meter per second squared. Okay? And that the spring constant is just, I'm just going to assume 1. I didn't really talk to you about dimensions yet. But so this block is going to hit the spring. How far is it going to compress this spring? How can we determine that? What do you think? Yes. Okay, so the kinetic energy of the block is 1/2 mv squared, which is just going to be 1/2 of a joule, right? Since we have V is 1, mass is 1, so we get 1/2 times 1 times 1, so we just get 1/2 of a joule. Okay, what else do we need to do?
Set that
Okay, and so we set that equal to, so this is going to come in here. It's going to change that velocity, right? It's going to start off at 1 meter per second. It's going to hit that spring, and then it's going to start to slow down because that spring is going to do some work on that object, right? Or you can think about that this is doing work. We're going to just assume that this is going to do work on the object, right? So that has to be equal to, therefore, 1/2 k x final squared, right? So if I solve ½ k x final squared is equal to 1/2 joule. And so the x final is equal to 1 joule over k square root, which is just 1. Okay? Okay, so that will compress that spring a distance of 1 meter. It's a very weak spring, even though it had very little velocity. It took a while for it to come to rest. So that's when it goes to its maximum displacement, and when it's done that, then it has moved a meter. And I should say this is minus 1 meter if we're thinking about it in terms of this as the axis. All right. Now, so let's consider work done by a variable force. Now, this was already the first This is the first example of work done by a variable force because the force is changing as a function of position. But more generally, work is equal to the integral of f of x dx. So in one dimension. So if I know what the function is as a function of position, then all I need to do is go from my initial position to my final position of that function and just integrate that. Okay? So essentially what we've drawn in the previous example was we had a spring being compressed. And in there, the function as a function of position is what would it look like on a graph? Here's x, here's f of x. What would a spring look like on a graph? Sorry? Okay, good guess, but it's not, that's the motion that it would have. It would have a sinusoidal motion. And we'll actually come back to that. But if I think about the force, what does the force look like as a function of its position? Yes? Okay, good try again, but it's not a U. Yes?
Is it upside down?
Good try again, but it's not upside down yet. Yes?
Straight line.
Straight line. And what would it slope? Negative what? Negative k. Good. Right? So many of you are familiar with y equals mx plus b as a straight line. If you think about force, that's what we have. Y equals mx plus b, but b is the y-intercept, and b in this particular case is 0. And so we see that as far as that's concerned, that this is going to look like, if I were to draw this, it's going to look like something going from the 0 and having minus k as a slope. Right? So I think I can do something along this line. But what I can think about is so that's one particular graph. Now let's just say I have something that I know, for example, its functional form. Now if I look at this, right, this has parts of the force. This is always a positive force, right? If it comes down, it has some sort of negative. But if I look at any one of these intervals here, and I say, well, I'm going to look at such a small interval. Actually, it might be better to look at it up here. I'm going to look at a really small interval over which the force doesn't approximately change. Right? In this region, the force doesn't change. And so I can use my regular constant force result times the width, which I call delta x, times this force f of x, and that is going to be what we would call delta w, right? That would be delta w is equal to f of x at that particular x, delta x. So if I just look at that and then I sum up all of those contributions, then I get the total work done on the system. So if I keep doing this, basically I see that I end up getting this work is equal to the integral of f of x dot dx, where all we've done is we've said that instead of delta x being something finite, we make it infinitesimally small, and so it becomes a perfect approximation of that force at that point, rather than taking some sort of average force at that point over that region. So all we've done is taken delta x to 0, and then we get this relationship here where we've integrated over that in all dimensions. Okay, so, let me just make sure. Okay, good. And in 3 dimensions, what you can think about is that dW is just, if I look at what I did over here, is delta W is F dot delta X, F of X dot delta X. What I can say is that is just because then the force dotted with some little, dotted with the displacement vector in 3 dimensions, right? And so I see that this just becomes, sorry, F of X dx plus F of Y dy plus F of Z dz. And so therefore, if I integrate the work going from some Ri to R final, which is just saying I'm going from some initial point to some final point, and then finding out what the total work is, then that's just going to be the integral of F of X Fx dx plus integral F of Y dy plus integral of F of Z dz, where this goes from X initial to X final, this goes from Y initial to Y final, this goes from Z initial to Z final. Okay. Now there's a lot to cover in this chapter. So going back to 1 dimension. So if I just look at this and I say work is equal to the integral of F of X dx, well, what we can just say that we know that this has to be equal to MA dx. And now A is a function, the mass isn't changing as a function of position, only A is, right? So we don't need to worry about what the mass is, how the mass is changing as a function of position, only what A does. We will actually consider that later when we talk about, for example, like rockets. But for right now, what we're going to say is mass is constant, but A is changing as a function of position. And so what we can say is that this is equal to M, but we know that that is just simply dv dt, because it's the change in the velocity as a function of time. Now, if you remember from the deep dark recesses of calculus, that you can use, for example, the chain rule, you can rewrite this as dv dx dx dt. And if you want to think about that, all I've done is you can think about what I did is I simply took a dx out and put a dx in the numerator. It's like I multiplied it and divided by a dx, and so therefore I could bring it out in this way. So, but this is just, dx dt is just the velocity, right? So we see that this is just m, and then dv dx times the velocity times dx. Then, this may seem a little funny, but what we can do is then cancel out our dx's again, and what we're left with is m times v dv, m times v dv as our integral for doing the work. Okay, now this is a more generalized form than what you have seen, right? You can see, for example, that if I just take this, I get the take the integral of that, right? I get, for example, I get this 1/2 mv squared, what we originally got for our kinetic energy. Okay? Make sure. So let me just say this goes from the initial to the final, and we see that this gives me 1/2 the 1/2 m the final squared minus 1/2 m the initial squared. So we can see that the work done on the system, even for a variable force, ends up giving us once again, the change in the kinetic energy, which is a pretty neat result, right? So even if it's a variable force, the work done on that will change the velocity in this way, rather than the simple equation that we did where we just used the kinematic equation. Okay, one last thing, which is power. Power, instantaneous power, is the time derivative of the work with respect to time. Okay? So let's think of a simple example. We know that, for example, let me write this on the board so you don't get confused. For a constant force, right, which we considered earlier in the class, work is equal to just the F dotted with X. Now I'm going to use X for a reason, because it'll be more familiar to you when we do derivatives. Okay, so I'm going to say work is F. Now X is the displacement rather than D that we did before. But if I look at that, and I take the time derivative, so that means power is equal to d dt of F dot X. And so we can see if this is a constant force, then we can see that the ddt isn't changing the force. And so we can see that this then becomes F dotted with dx dt, which is just F dotted with v. Okay? So that's how we would determine the power of that particular system. So what you can think about is the power is the time rate of change of the work being done on the system. Questions? Yes?
First works in 3 dimensions.
Yes.